When working hot metal, like a steel bar, it's very important to remember that after shaping, it's by no means fit for the job. Take this chisel. It's being forged into shape by a traditional method. But before the chisel can be used, it must be heat-treated. This is done by heating it and then quenching it in water. This hardens the chisel, but unfortunately, it'll also make it brittle. So brittle that if it's used without further treatment, it'll break. It needs not only to be hard, but tough as well. It has to be tempered. To do this, the smith cleans the surface of the chisel with an abrasive paper and then reheats it, this time to a lower temperature. Then he quenches it in water. This makes the chisel less brittle, but it also robs the metal of some of its hardness. To show you what happens, let's look at a small carbon steel rod. The rod can be flexed easily in the hand, and you can see how elastic it is. When the rod is heated in a furnace to red heat, then cooled as quickly as possible in water, it will become hardened. So hard, in fact, that a file won't make any impression on the surface. It'll just skid over it. But unfortunately, the rod has now become brittle. In this second experiment, an identical rod is heated in the furnace to the same red heat. Then it's cooled very slowly by immersing it completely in vermiculite, a process known as annealing. The metal will now have good ductility and will be soft. You can mark it with a file with no trouble at all. It'll also bend easily, but after bending, lacking elasticity, it remains bent. In a third experiment, the rod is again heated to the same temperature, and then it's quenched rapidly in water. That makes it hard and brittle, just as in the first experiment. Then the rod is put back into the furnace, and this time heated to a lower temperature. After this, it's cooled slowly in vermiculite. It could also be cooled in air. This process of heating and cooling is known as tempering. It's a carefully controlled compromise between toughness and hardness. The rod doesn't mark too easily with a file, and it can be flexed in the hand. The extent to which any steel may be hardened is largely dependent on its composition when it was made in the furnace. The amount of carbon present is most important. Sometimes the addition of transition elements, such as chromium, can also affect its behavior. In fact, adding such elements produces what's known as an alloy steel. But it is the amount of carbon present and the rate of cooling of the hot steel which exercises the most influence. To understand how the carbon content and cooling rate affect the steel's properties so dramatically, we need to look more closely at its structure. Let's start with that steel rod experiment. Before any heat treatment, it consists mainly of atoms of iron arranged in a body-centered cube. It's called alpha iron. And there are 9 atoms of iron, 1 at each corner and 1 in the center, which we've shaded for clarity. Under the microscope, it looks like this. Here, there are 2 types of crystals. The rather plain ones are pure iron, ferrite. In the others, the carbon has joined with the iron to form iron carbide, and this combined with the rest of the iron produces a laminated structure looking like mother of pearl. It's called pearlite. When the metal is heated, it reaches a temperature at which the body-centered cubic arrangement changes to the face-centered cubic type, known as gamma iron. We've shaded the central iron atom on each face of the cube. As the rod is heated and the carbon is taken into solid solution, the laminated structure of the pearlite changes. In this form, it's known as austenite. The change from one form to the other is easily reversible, from the high temperature, face-centered cubic, to the room temperature, body-centered cubic, from austenite to ferrite and pearlite. Now, instead of cooling slowly, if the rod is cooled rapidly by quenching in water, the carbon atoms have no time in which to come out of the solid solution. The resultant structure can be explained by considering two face-centered cubic arrangements. As the metal cools, it can only revert to a distorted body-centered cubic arrangement due to the enforced presence of the carbon atoms. The structure is known as martensite. It is this distortion that gives rise to the hardness and brittleness. Under the microscope, it looks like this, with its characteristic needle-shaped crystals. In practice, few steels are used in this extremely hard and brittle martensitic condition, and the reheating of the rod again to a lower temperature, tempering, removes some of the brittleness, yet retains much of the hardness. What's happened in the tempering process is that a small amount of carbon from the distorted arrangement has been allowed to come out of the solid solution. The temperature at which alpha iron, ferrite and pearlite, completely changes to gamma iron, austenite, is directly related to the amount of carbon present in the steel. So, being able to predict when these structural changes occur is of extreme industrial importance. If temperature in degrees centigrade is plotted against the amount of carbon on a graph, then, whatever the concentration of carbon, this change begins to take place at 723 degrees centigrade. If the temperature at which the complete structural change occurs is plotted, we can see that it varies according to the amount of carbon present. As the level of carbon increases, the temperature for the complete alpha to gamma change falls to a minimum of 723 degrees centigrade at 0.83% carbon. At this point, the structure of the steel is purely pearlitic. Above this critical carbon content, the temperature rises again. Joining these points together yields what's known as the iron-carbon equilibrium diagram. Here we've only considered steels with a carbon content of up to 1%, which are the majority of steels used in manufacturing industry. There are two very important bits of information on this graph. The upper critical point and the lower critical point. In practice, to get a fully hardened structure, the carbon steel must be heated to a temperature just above the upper critical point before quenching, and it must be tempered well below the lower critical point. So, for a given carbon steel, it's possible to predict the limits of any heat treatment process. As a quenching medium, water is cheap and plentiful. But because it cools the metal so rapidly, there is a danger of cracking or distorting the metal. That's why oil is frequently used. The cooling effect is not as rapid. As a result, the component will be slightly less hard, but the risk of distortion and cracking is greatly reduced. These components were forged from a 0.4% carbon steel. Now they're ready to be heat treated. First, they're loaded into a gas-fired furnace and heated to a temperature of 860 degrees centigrade. This is just above the upper critical point for a 0.4% carbon steel. The time they're in the furnace will depend on the number of components and the thickness of the material. These conrod caps will be left in for 1.5 hours. After this time, they're taken to be quenched in oil. The conrod caps are agitated in the oil during quenching, and this helps to cool them uniformly. After the surplus oil is drained away, the components are ready for tempering. This is done at a lower temperature, 580 degrees centigrade, and it's well below the lower critical point for a 0.4% carbon steel. After an hour in the furnace, they're left to cool in air. This complete heat treatment process improves the hardness from 229 to 255 on the Burnell hardness test scale. Sometimes only part of a component needs to be heat treated. The teeth of this gear wheel require hardening because they are subjected to extreme wear. It's because this steel contains carbon that the theory of the iron-carbon diagram can be used. This technique is called flame hardening. A battery of jets burning propane or a gas mixture heats the surface to the required depth. Following behind is a similar battery of water jets, which cool the surface very rapidly. The result is that a layer at the surface is hardened while the body of the material remains soft and ductile. Induction hardening is a similar technique. The component is placed into a coil which has been preformed to the appropriate shape and through which an electric current flows. The coil becomes the primary of an electric circuit, with the workpiece acting as a secondary. The heat is generated solely by induction. The amount of current passed through the coil and the time the component spends in it are adjusted so that the surface is heated only to the required depth and temperature. An oil quench follows the heating, leaving a hardened layer at the surface. Both induction and flame hardening produce high surface hardness on a particular part of a component, and there's less distortion than in furnace heating. A wide range of quenches can be used: water, oil, polyvinyl alcohols, and air blasts. But there are limitations. The components to be treated must be ferrous, and none of the methods are really suitable for very small pieces. In flame hardening and induction hardening, it's usual to follow the cycle by a low-temperature stress-relieving treatment. If, however, the material from which the component is made contains a low amount of carbon, then the surface can't be hardened by simply heating and cooling. Here it's necessary to add additional carbon to the surface. It's known as a carbon case, and the process is known as case hardening. One of the oldest ways of adding carbon, it's called carburizing, is by the pack method. Here, mild steel rings are packed together with a charcoal mixture in a box. Then the lid is sealed with fire clay. The box is placed in a furnace at 920 degrees centigrade for some 7 hours. It's worth looking at the iron-carbon equilibrium diagram to see the effect of these conditions on this mild steel ring. Because carbon has very little solubility in the low-temperature, alpha form of iron, carburizing must take place at a high temperature just above the upper critical point, where the solubility of carbon is greater. As the material is very low in carbon, this means quite a high temperature. This, with the time in the furnace, will determine the depth and penetration of carbon into the surface of the component, as seen in this cold cross-section. But because of prolonged heating in a high temperature, grain growth occurs. The high carbon case will have a coarse, crystalline structure, and it has a tendency to crack under stress. This coarse grain has to be refined, and the case hardened. And this is the next stage in the process. After cooling, the rings are heated in a molten salt bath at 780 degrees centigrade for half an hour. The temperature has to be above the upper critical point, but it is lower than the original carburizing temperature, since there's now more carbon in the surface. After heating, the rings are quenched in water. So the case is hard and the grain refined, meeting this particular customer's requirements. It is possible to case hardened components without creating such coarse structures. These spindle shafts are made from a low-carbon steel. After preheating, they are carburized by immersing them in a liquid bath of sodium cyanide and sodium carbonate, which also contains a little sodium chloride. They're left in the melt at 900 degrees centigrade for 1 hour. This is time enough to impart a thin carbon case, but not long enough to produce a noticeable grain growth. After an hour, they're quenched in water to give the required hardness to the surface and a clean finish to the component. Different parts of a component will frequently require varying degrees of hardness. The teeth on these low-carbon steel gear shafts, for example, need to be very hard because they'll have to stand a lot of wear. The core of the material needs to be tough, and the thread that's in the center of the shaft must remain soft so it won't break when used. To prevent any carburizing of this thread, it's blanked off completely with fire clay. The method to be used here is called gas carburizing. In essence, the parts are placed in a furnace, heated to the required temperature, and a carbon-rich gas introduced. Again, the depth of the case will depend on the temperature of the furnace and the time the piece is left there. The equipment is in 3 parts: an oil quench tank, an outer compartment or vestibule, and an inner furnace. The inner furnace for the gear shafts is at a temperature of 900 degrees centigrade, and it's here that the carburizing will take place. The gear shafts are cleaned, degreased, and loaded in a wire basket, and this is pulled on rollers into the outer vestibule. Once the door is closed, all the air is purged away and replaced by what's known as endothermic gas. It's essentially a carrier gas and is virtually neutral. It won't add any carbon to the surface or remove any carbon that's already there. It's there solely to carry the carbon enrichment gas. This purging takes 15 minutes, and then the tray and its contents are passed into the furnace at a temperature of 900 degrees centigrade for carburizing. The carburizing gas here is a mixture of cracked methane and air. The gas is passed over the components, completely covering them for 10 hours. The case is then carburized to a depth of 1 millimeter, and the surface now contains 0.8% carbon. The original material contained 0.1% carbon throughout. An X-ray photograph indicates the type of effect achieved. The carbon case shows up as white. The major disadvantage is that the component now has a coarse, crystalline grain structure. This has been caused by the length of time spent in the furnace at this high temperature. So, after cooling slowly in the outer vestibule, the next stage is to refine the grain of the bulk of the material, the core. This, remember, contains 0.1% carbon, as the original did. Using the iron-carbon equilibrium diagram, it's possible to predict the required temperature. It's 880 degrees centigrade for 3/4 of an hour. Then it's into the outer vestibule again for slow cooling. The coarse grain structure of the core has now been refined and looks like this. The final stage is to refine and harden the case, so it's back into the furnace at a lower temperature because of the higher carbon content, 0.8%. This time it's 760 degrees centigrade for 3/4 of an hour, and then it's oil quenched. This refines the grain of the case and hardens it. The end result is that the gear teeth are hard, the core is tough, and the thread, after removing the fire clay, will still be soft. The whole system is controlled by a mini-computer. Different sequences for different materials can be programmed by changing the microprocessor. Hardening the surface of ferrous metals can also be carried out by introducing nitrogen into the surface of the component. Nitriding resembles carburizing in that the steel is heated for a time in the hardening medium. For carburizing, it's carbon. In nitriding, it's nitrogen. But for nitriding, it's important to have special alloy steels which contain small amounts of metals like chromium and vanadium. The nitrides formed from these metals hardens the surface of the steel. One of the latest techniques is called plasma ion nitriding. Ion nitriding is the introduction of nitrogen ions into the surface layer of an alloy steel component under a low-pressure, high-voltage condition. Treatment conditions are accurately controlled to produce, it's claimed, specific structures not found in normal gas or bath nitrided steels. The enthusiasts say that plasma nitriding produces more desirable results than conventional nitriding processes. The types of components suitable for plasma nitriding are those which have to withstand high wear conditions and yet remain accurate in form. Things like internal and external gears, crankshafts, and rolls for the coal industry. After cleaning and degreasing, the components have to be degassed to prevent localized arcing during nitriding. So they're loaded into a vacuum chamber, which will also contain the plasma. Care is taken to place the components in the furnace so that effective electrical isolation is achieved. Then the seals on the chamber and its door are cleaned and greased to ensure a good vacuum. The process can be carried out using either pure nitrogen or mixtures of nitrogen with hydrogen or suitable hydrocarbons. Treatment times vary between 10 minutes and 20 hours, depending on the grade of steel and the depth of nitriding. The components are connected as the cathode and the furnace walls as the anode. Under this potential difference, the molecules and atoms of the treatment gas, in this case ammonia, are excited and ionized, producing a luminous phenomenon known as the glow discharge. The positive ions of the treatment gas are accelerated to the negatively connected workpiece and hit its surface with tremendous kinetic energy. The release of this energy heats up the workpiece, and the ions are occluded into its surface. So the chamber doesn't require a separate heating system. The major advantage, it's claimed, is that the structure and grain size of the material remains unaltered, the hardening being caused by lattice distortion and a fine dispersion of precipitates. The last decade has seen many innovations in surface heat treatment, which has led to an improvement in product quality and a more efficient use of energy. A number have been well tried and improved on over the years, while others promise much for the future.